to the second session in Fundamentals of Electrical Circuits, where we discuss the solutions of DC networks, which have essentially only independent DC sources. Okay, the sources could be current or voltage sources, but they are independent and so are not dependent on any other circuit elements. Okay, and earlier though we discussed Kirchhoff's law, and the Kirchhoff's laws are always going to be fundamental to any kinds of solutions. Some simplifying methods like nonlinear methods, not really linear, because we'll be fitting together things and trying to find answers. Okay, so let's look at some of the nonlinear circumstances also that are there, and there also we'll try to do some smart jobs such that the solutions can be found out. Okay, so question number 1, wherein we are having a 10-volt battery with an internal resistance of 1 ohm is connected across a nonlinear load. Okay, still Kirchhoff's law is applicable. Kirchhoff's laws are applicable to linear or non-linear or any kinds of elements. Okay, across a nonlinear load whose VI characteristics is given by 7I is equal to V square plus 2V. Okay, the current delivered by the battery is, of course I. Okay, so we can and that current, because the whole setup is in series, we have a 10 volts battery with its internal resistance in series with it, and then the nonlinear resistance which has a current as given by its voltage current relationship I is equal to V square plus 2V by 7. Okay, so now we can write out the equation as equal to 10, that is the voltage applied is equal to the two drops, one over the linear one, the other over the nonlinear resistance. Okay, so I into so we are having the voltage that is I into 1. Okay, or 1, that is the 1 ohm resistor which is linear. Okay, so 1 ohm into I, where I is the same as equal to V square plus 2V by 7, and then the voltage across the nonlinear element, which is of course V. Okay, there's no doubt about it. Okay, because the voltage current relationship is given there. Okay, that's all. The current is actually derived. Okay, so we have now solving this, you see that we have a quadratic equation wherein we are having V square plus 2V as also plus 7V, that is 9V, minus 70 equal to 0. Okay, solving it, you can see that that V is equal to you get V, and when you substitute, okay, you get V. When you substitute for it, you get what is called as the current. Okay, or in other words, you're solving. You can get the current as equal to 5 amps. Okay, moving on to a third problem, a similar one. Okay, this was a recurring question in the gate contest. Okay, to read it, okay, no figures are given. A 3 volt DC supply with an internal resistance of 2 ohms. So 3 volts with an internal resistance of 2 ohms in series with it supplies a passive nonlinear resistance characterized by the relation VNL is equal to INL whole square. Okay, so the voltage is proportional to the current square. The power dissipated in the nonlinear resistance. Okay, since answers are given, this is an MCQ type of question, so we try to go for the look at the answers. Okay, so the answer, the first answer 1 seems to be good because it's 1 watt. Why? Because if that is the case, then V and I can be the same as equal to 1. Okay, that is we have V into I, which is 1 into 1. So and I square, which is 1 square, it's also equal to 1. So there is a goodness in that, and you can just fit and see. Okay, so if we are having 3 volts, and then if you have if a current I emerges out of it, which is equal to which creates a drop of 2 volts across the 2 ohm resistor. So 1 volt is now available. Okay, so 1 ampere into 1 volt is equal to 1 watt. Okay, so it's easy to fit and see, but of course the relation is also the same as equal to there is 3, and there is the applied voltage 3 is equal to 2 into I plus I square, because the voltage across the nonlinear element is given by I square. Okay, so solving it, or by just fitting together, we can see that that I is equal to 1 and V is equal to 1. So together wattage is equal to 1 watt. Okay. Okay, so we did the third problem. So now let's go to the third problem. In the figure, we have 300 volt as also a resistance R and a current I flowing through it. Okay, so we don't have internal resistance, and it is said that the resistor is, okay, so I am reading the problem, the value of resistor R is 25 plus I by 2. Okay, so now with 25 plus I by 2, if you multiply by I, you should get the voltage across it, which is equal to 300 volt. Okay, so 25 I plus I square by 2 should be equal to 300. Okay, why not try 10? Okay, because 10 is a good value. Okay, so you can see why do we do that? Because 300 and 300 volt, to come nearer to 300 volt, to 25 I has to come nearer. Okay, or in other words, you can say that 25 into 10 gives us near around the value. The rest now needs to be compensated by I square by 2, or say 100 by 2. So 50 plus 250, 300 volt. Okay, so the equation is the same. It's the same as equal to 25i plus I square by 2 equal to 300. So you can solve the quadratic. Okay, or fit and do the problems. Okay, so in this case, in this session, essentially ease of solving problems is taken care of. Okay, question number 4. We see a 100 volt source, and we see 12 ohm, and we see a very good 14 ohms there, and we see 4 amps flowing through the unknown resistor R. Okay, and what is asked is, in the circuit shown, what value of R will result in current I is equal to 4 amps. So 4 amps needs to flow through R and create a voltage drop, which should be somewhat related to 14 ohms. Okay, so what are the better results? So we see that R is equal to 7 ohm is good, because 7 for the 28. So we can see that 14 ohms will now carry 2 amps. Okay, just fitting the data. And 3.5 is also good. Okay, in that case you will get 4 into 3.5 is equal to 14 volt. So it's so now 14 ohms that 14 ohms creates a voltage drop equal to 14 volts, so 1 ampere. So together 5 amps. Okay, so together 5 amps means 60 volts across the 12 ohm resistor, which requires a large amount of voltage across the 14 ohm. So the other option is better, because now we see that 4 into 7, that is 7 ohm for the resistance R, then 28 volts, which means that 2 amps flows through the 14 ohm resistor. So 4 into 6 ohms flows through the 12 ohm resistor, creating a voltage drop of 72. 72 plus 28 is equal to 100. Everything fits together. Okay, so this is what I suggest when you are you have to have a look out for the best kinds of numbers that are given. Okay, and based on the numerical value, so you can easily solve the problem. Fifth problem, we have a current source IA 5 amps. It diverges into R2 and R3. R2 is 3 ohms, R1 is 4 ohms. Then then we also have a current source on the other end. There, 3 amps flow downward, and another I3 flows downwards through the 5 ohm resistor. Okay, so it's a lot of things there, and what is asked is that in the circuit shown, the currents I1, I2, I3 through 3 resistors are respectively. So only currents are required. The resistors are immaterial here. Okay, so after a first glance, it's always good to look at the answers, and you see certain values, and so read it and then realize that 3, 4, 5, whatever they are not going to be important. Okay, as it is, the value is not good enough. Okay, so what do you see? That I1 and I2 should be equal to 5 amps. That is of course Kirchhoff's current law. Okay, so so we are given I1, I2 and I3 through the 3 resistors are respectively. So add the first 2 and see if it's 5. Okay, of the given 4 answers, only A matches the situation, and then you can look for the third one also. That is I3. If it is minus 0.08, it means that it is going to come. It is going to come to the node wherein the current source is attached, and then I2 and I3 together should be equal to 3 amps. That's right, 2.92 plus 0.08, because it has reversed the direction. It gives you 3 amps. Okay. Problem number 6. The current in the 1 ohm resistor, the network is shown. Okay, so network as shown is what? Okay, so we have a 2 volt source and a 2 ohm resistor. What do we immediately recall? We see that it is equivalent to a 1 ampere source with a 2 ohm resistor connected in parallel. Why do we go for that? Because we see all 2 ohms there. So now we are having another source, 3 volt and 2 ohms. That gives rise to 1.5 amps. So 1.5 and 1 amps together, 2.5 amps comes to the top, and then we are having the 2 ohm resistors in parallel, and then we are also having 2 amps on the other side. So there is a confluence of so many currents. There is 1 ampere, there is 1.5, and then there is 2. So in total there is a total amount of 4.5 amperes, and then there are 3 resistors in parallel. 2 together, 2 are 2 ohms and 1 is 1 ohm. Okay, so now you can split the current into 2, as one going through the 1 ohm resistor, another going through the 2 ohm and 2 ohm in parallel, giving rise to another. Okay, so 4.25 by 4.5 by 2 is going to give you 2.25, and if you want, so that gives you the current to the 1 ohm resistor. If you want to have any other values, you can again further divide by 2 to get the current through the 2 ohm resistors if required. Okay, so the current, the 1 ohm resistor, the network is shown. Okay, so it is simple. I hope the fitting together and doing problems is also clear to you. Okay, so now let's go to another kind of problems. Okay, wherein again all these aspects that were talked about, which makes solutions of circuits simpler, will be dealt with. Okay, so question number 7. We have 10 volt source, we have 5 amps, okay, and we see that this 5 amps is always going to flow through the 2 ohms resistor because they are in series, and what could be asked could be the voltage V out across the 5 amps. Okay, so if V out is going to be positive, then this is delivering power. In that case, the 10 volt source might be absorbing power, okay, or else the 2 ohms will require a lot of power. Okay, so let's see what it is. In the circuit shown below, the voltage and current source is ideal, the output voltage V out. What is it? Okay, so let's see. 5 amps flows through the 2 ohms resistor and creates a drop there with the right terminal positive. So we see that that's equal to 10 volts. So 10 and 10, 20 volts. So 20 volt together come on across the 5 amp source, giving rise to 20 into 500 watt output. Okay, and the resistor demands only 25 to 50 watts. So the remaining 50 watts is now going to be fed to the 10 volt source from the 5 ampere source. Okay, so the current source is now charging the voltage source, okay, through the 2 ohm resistor. Okay, a very practical situation. This is always what is being done in the charging circuits. Okay, moving on to problem number 8. A 6 amp source and a 3 volt source with a 4 ohm resistor in series with the 6 amps. What do you do to it? Discard it. Okay, and there is a 3 ohms resistor in parallel to 3 volt source. Discard it. So now it's very simple. A 6 amp source is now going to be connected parallel to 1 ohm. Okay, be brave and just discard the earlier 4 ohm, and now 6 amps in parallel to 1 ohm. Okay, so now let's see what is required, and discard the 3 volt source. So now we are having a very simple circuit with a 6 amps in parallel to 1 ohm resistor and a 2 ohm resistor and a 3 volt source. Perhaps this current source can be converted into a voltage source. Okay, what is the voltage at A? So what is asked is what is the voltage at A. So we see that now there are two currents, there are two current possibilities there. One is of course that 6 and 1 together give rise to together give rise to a 6 by 1, that is 6 ampere to node A. Okay, at the same time, now after removing the 3 ohm resistor in parallel to 3 volts, we are having another current source where 3 volt and 2 ohm together, the 2 ohm in series with it together gives rise to another current source which is equal to 1.5. So together to A, two types of current sources come together, and that's equal to 7.5 amps. Okay, and what happens to that current? Okay, it now flows through the 2 ohm resistor which was earlier in series with 3 volt source. Now it becomes parallel to 1 ohm. Okay, so now we are having a so what's the current through the 1 ohm resistor? It's given by 7.5 into 2 divided by 2 plus 1, current division rule, and so we see that it's equal to 5 amps, and then when it flows through 1 ohm it becomes 5 volt. Okay, very simple. Okay, so this is an important concept that you can use, wherein any resistor in series with the current source can be removed, and thereafter you see that a current source is now in parallel to a 1 ohm resistor. Thereafter it can be converted into a current source again. Similarly, a voltage source which is in parallel with an impedance, the impedance has been removed. Thereafter now the voltage source has become series with a resistor which can now be converted into a current source, and then both the current sources pump current into the same node A, and then the current diverges through 1 ohm and 3 ohm, as 1 ohm and 2 ohm, as simple as that. Okay, problem number 9. Okay, we have done this earlier, but we'll do it in a different manner this time. Kirchhoff's voltage law can be, current law can be used. So in this circuit, which has 10 volt, okay, of which we know that this 10 volt is not going to supply any power. Still, we say that this 2 amps and 1 amps together now come to the node from node connecting to the 10 volt source, and then it flows as I plus 3. Okay, so let's say that we are having I coming from the voltage source. So I plus 3 flows into the 1 ohm and 1 ohm resistors in series. So that is equal to, that creates a voltage drop equal to 2 plus 6. 2i plus 6, and then 1 ampere goes away. So we have the remainder as I plus 2 flowing in the lower 2 1 ohm resistors. So that gives rise to another 2i plus 2i plus 4. Okay, so now 6 plus 4 is equal to 10, so I is equal to 0. Okay, so obviously I is equal to 0, which means that the 10 volt source is just keeping the potential across the top node and bottom node as equal to 10 volt, but it is supplying no current. Okay, so there, so it is so the power delivered is equal to 0. Okay, moving on to problem number 10. Okay, let us read it carefully. Quite a lot of English is there. A bench top DC power supply acts as an ideal 4 amp source. Okay, what do you mean by an ideal 4 amp? 4 amp remains constant. Okay, as long as its terminal voltage is below 10 volts. So a diagram is simply drawn. The diagram can be drawn in your mind, wherein the 4 amp remains constant until the voltage. So we have a current voltage diagram here. It's not a waveform with respect to time. Okay, so current remains constant, and then at 10 volts, what happens? Okay, beyond this point, it begins to behave as an ideal voltage source. Okay, so thereafter, the 10 volt is remaining constant. Okay, for all load currents going down to 0 amps. Okay, when connected to an ideal rheostat, find the load resistance value at which maximum power is. Okay, so what is the maximum power point? This is true with respect to the solar power as well. You have a point wherein 4 amps and 10 amps are coming together, and there 10 by 4 is going to be the impedance that has to be connected such that maximum power can be transferred. Okay, and yeah, that's exactly what is asked. When connected to an ideal rheostat, find the load resistance value at which maximum power is transferred and the corresponding load voltage and current. So the ohmic value is 2.5, the voltage is 10, the current is 4, and I suppose the answer that corresponds to it is equal to C. Okay, yeah, so by moving on to the 11th problem, we have a circuit shown with a 5 amp source pumping current through a network wherein the top node and the bottom node have been connected together or shorted together, making two separate circuit elements parallel. Like for instance, the 2 ohm and 2 ohm are going to be in parallel. Okay, across the 5 ampere source, and we also have 3 ohm and 6 ohm in parallel. Okay, then thereafter they continue with the 7 ohm and return back to the source. Okay, so what is asked is the current flowing through the 7 ohm resistor between P and Q. Okay, so what is the current? Okay, so we are having the 5 amps now dividing into 2. One circuit is made up of 2 ohms and 2 ohms in parallel. So that's one part of it. So 5 into 1, because the current that is asked is through the 7. Okay, so 5 amps into 1, and then we are having what is called as the other part. Okay, what is the other? We have 3 and 6 in parallel. So 2 times 6, 3 is 6. So we have 3 into 2 by 3, that is 2 ohms, and then 2 ohms and 7 ohms in series, so 9. Okay, so 5 into 1 divided by 9 plus 1, or in other words 0.5 amps. As simple as that. So we have used mostly the tricks of the trade to fit together data and arrive at solutions. I hope the different ways in which we fit together are clear to you. So be it a linear or non-linear resistor, the Kirchhoff's laws are applicable, and in most of these cases it will be possible for you to solve without solving the quadratic, but the quadratic is always available such that you don't make mistakes. Okay, and Kirchhoff's current law and Kirchhoff's voltage law are always going to help you to the maximum extent to solve circuits that look complex but are actually very simple, especially because the laws hold true whatever happens. Okay, and we also saw that the same old understanding that whenever we are having the current and voltage in the same direction, any such network or a full network gives rise to a power developed by the source, and then the other sources, if the current and voltages are in opposite direction, they absorb this power developed by the source, and every network with respect to the power happenings are going to be self-contained. Whatever is produced is consumed there itself. Okay, so I suppose with that again I harp on the same old thing, that is a current source in series with the resistor. Remove it. Okay, just remove it and then look after the rest. Okay, so if you see another resistor now in parallel with it, okay, that they can be combined together for source transformation to a voltage source. Okay, similarly a resistor in parallel to a voltage source can be removed. Okay, and then if you encounter another resistor in series with this new voltage source or this unencumbered voltage source, then you can together make them into a current source. Okay, and but of course the resistor will now come in parallel to the current source. Also the directions need to be taken into consideration. Okay, so the pointer will always show the positive part of the voltage that results as a result of current to voltage transformation, and the positive terminal will be the terminal through which the current is going to emerge when a voltage source is converted into a current source. Okay, so thank you.